All right. So.
All right. So our talk is by Pablo, and yes,
Yeah.
and he's going to tell us about integrating graphical proofs in Coq.
Okay. So just a few adjustments. Sorry, it was working well earlier, so yeah, I guess it will be fine. So, sorry for the delay. I'm going to show you a joint work with Benjamin Werner and Kostya Chaudhary about integrating graphical proofs in Coq. So in the first part of this talk, I'm going to explain what I mean by graphical proofs. And in the second part, I'm going to explain this coq-actema system that we built, which integrates them in an existing Coq development. So the context of this work is, like, the overall aim is to make proof assistance easier to use. So first, for newcomers to the world of proof assistance, by making the interface more intuitive and discoverable, but also we hope that some features will be of use to experts by making some tedious tasks easier to perform, like selecting subterms or applying or searching for lemmas. So for now, this work is in the setting of intuitionistic first-order logic. There are two main reasons for that. The first reason is that most proof assistants have this logic as a subset of their logical framework, so this should make our approach applicable to more universally. And the second reason is that to define the semantics of our graphical actions, it was easier to do so in first-order logic. And of course, this is work in progress with many design decisions subject to changes, and of course, buggy implementations. So without further ado, I'm going to make a quick demonstration of coq-actema, the system that we built. So basically, you have this. On the left, this is the usual window of your Coq IDE. In my case, it is VS Coq. And on the right, you have this interface. So, okay, I'm just gonna go back a few steps. So basically, the idea is that the interface on the right, which is called Actema, is an interactive proof view. So here I have some very simple goal, like, so you can see here, I can just make it a bit bigger. So on the bottom, you have the usual proof view. So I want to show that if Socrates is human and all humans are mortal, then Socrates is mortal. So with tactics, I can just do this in a few tactics, like introduce some assumptions, apply, and then exact. Now I'm going to do this graphically with this tactic called Actema force, which comes from this line where I import some plugin. And here you see that the tactic sends the goal to the interface. So how does it work? You have green items which represent mathematical objects, basically assumptions whose type is of sort type, and blue hypothesis, and then the conclusion in red. And so what I can do is interact with these items, move them around on the screen, drop them, and you see that when I start dragging my conclusion, already the system highlights some part of the goal where I can use my conclusion. So here I can just bring it there. The system unifies the two occurrences of the mortal predicate, and when I drop it, it basically applies my assumption, and I get this new conclusion, which I can now finish the proof like this. So this was an example of a backward proof. I can also apply the same principle in forward mode. So same idea, I grab some item I want to use, and I bring it to the place I want to use it. So just like this, then I get that Socrates is mortal, and I can finish like this. So here you see in Coq that I can just type check the proof, and I have a proof term. And if I print it, it's ugly. But it works. I have compiled my graphical actions. Now, if I were to do a more simple example, just the identity function, I can do it actually with click actions. So I can double click on the red implication, then on the blue assumption, and I'm done. And here, if I print the proof term, you see this is just the identity function. So click actions give better proof terms, but are less interesting, as I'm going to show you. So from now on, I'm going to show some examples which are not necessarily provable, but I think this is useful to demonstrate the like Actema is useful in exploratory settings where the user is not sure or doesn't have the intuition about the probability of the goal, but still wants to sketch some partial proof. So here I can so the idea is that I want to simplify, like to remove the C and the B in the conclusion, since I have them. It's very small. I can zoom in maybe a little bit. So, or maybe not. I'm not sure. So basically, you're going to see the goal in. So, okay, I can just perform a bunch of tactics, which I have to know beforehand. But if I'm a beginner, it's not easy to guess. So graphically, I can just apply this the equivalent of these tactics by click actions. I can introduce my application, split my conjunction, then destruct, then exact, and then I can split again. So here you see that when I split, I get two sub-goals, which are represented by these little tabs. I can switch between them. And then I can choose left or right by clicking on the right location, and then finish the proof. Like finish the partial proof, sorry. So now I can't go further, so I need to click on the done button. And then I'm left with this goal in Coq, which is the same. And that's it. So I can redo the proof in a much more succinct way by just using drag and drop actions. Basically, I just follow my intuition. I want to use this C to justify this C. And when I do this, it will simplify the conclusion, like drop the whole disjunction, but leave the surrounding context in the formula intact. And yeah, I can do a second drag and drop. And like with just two actions, I've got the same result than with this whole bunch of tactics. Another nice features of drag and drop actions is the ability to make reasoning on somewhat equivalent formulas uniform. So in backward mode, for example, I can use these two versions of the same statements, codified and codified, in the same way. Basically, this is going to perform some kind of rewrite, where again I preserve the surrounding context at this junction, and I can of course do it with the codified version in the same way. If I were to do this in Coq, it would be a lot harder. Basically, I cannot apply directly the uncodified version. And all right, just minimize this. And so what I need to do is the only way to work around this would be to introduce a cut formula, which is quite complicated, then use some automation, apply clear, and yeah, this is not at all intuitive. I can do the same thing in forward mode. So here, it will perform some kind of partial application. So I do this, and then I get a new hypothesis where I have just applied partially on the second argument. And basically, you couldn't do this in Coq because you need to apply arguments in order. And the only way, again, to do this would be to use, okay, just skip this. Yeah, you would have to use an assert to get the equivalent things. So now we can work with quantifier also. So in Coq, when you want to apply some hypothesis, modulo some existential unification, this won't work right off the bat. So the apply tactic doesn't work. So the only way to do this is just, so you can either instantiate your quantifier and then apply, or you can use this mechanism of existential variables. But again, as a beginner, you wouldn't know necessarily about this. And you have to know all these variants of the tactics with existential variables with a little e in front of the name. Graphically, this is straightforward. Just bring it there, it unifies, and it works. You can also do the manual instantiation by bringing the object like this, and then finishing the proof. A more complicated example, which shows how these drag and drop actions can compose the semantics with respect to different logical connectives. So here I might want to perform some conditional rewrite under some quantification. And so you can try to do this with a setoid rewrite tactic of Coq. But again, you need to know about this tactic. And here it won't do exactly what we want. So if I show the second goal, here, you see that I need to prove that y is different than 0 for an arbitrary y. Whereas what I want is to prove it for a specific y, but I'm not sure which one it will be yet. I don't want to instantiate it. And so basically, graphically, this will just work as you expect. You bring the equality assumption to the place you want to rewrite it, and it works. And here you see, so a little problem of space, but yeah. You see that the side condition has been input under the quantifier. I can, but again, with drag and drop actions, it will be very ugly. But yeah. Okay, no, I cannot, sorry, because this is a partial. Oh yeah, okay. I didn't know about this. Show proof? Oh. Yeah. So you will understand later why this does this. But just a last example, which involves a bit of induction, which is what I like to do in Coq. So I'm going to show commutative of addition entirely graphically. Basically, I can select my conclusion, and then I have this contextual menu where I can choose some action. So I can perform induction, all right? Then I have two goals, base case, inductive case. I can, so here I can just rewrite the piano axiom for 0, and then introduce and reflexivity by double click. I can also, so inductive case, here I want to simplify first because Coq is able to compute on the left of addition. Then I can apply the induction hypothesis and basically apply the other piano axiom and then reflexivity. And I can type check all of this. So that's the demonstration. So to summarize the features of this graphical paradigm, the aim is to completely get rid of textual comments. So we want it to be fully graphical, but since it's in first-order logic, of course, some goals in Coq won't translate correctly. So this is a long-term goal. And in one slogan, a graphical proof like this is just a sequence of gestures. And this brings some benefits. So different modes of reasoning are captured by the same syntax. So click actions correspond to introduction, elimination rules for connectives, and drag and drop actions to backward and forward reasoning. And this whole system of actions is solved and complete for intuitionistic first-order logic. Now I'm going to talk quickly about the overall architecture of the Coq IDE system. So basically, you have on one side the usual Coq system with the IDE, which mediates between the user and the kernel. And the other side, you have the interface of IDE, which is an Electron application. And so we've added to the kernel, on top of the kernel, a plugin written in the kernel, which handles the communication with the interface, as I will explain shortly. And the whole thing, of course, is using web technologies. And the backend of the interface actually is written in OCaml, but using JS of OCaml to transpile it to JavaScript. So the basic idea of the protocol is that the kernel will send a list of goals to the plugin, which will translate them to first-order logic goals, and then request from some source a sequence of graphical actions. So it gets the sequence, and then it compiles it to some tactic, which will be executed by the kernel. So if I focus on how we retrieve these actions, so actually there are two modes. So I haven't shown you, but there is a non-interactive mode where you can just retrieve the sequence of actions from some graphical proof database. So basically just currently it's files on the file system. So you send the current goal and then retrieve the sequence of actions. The interesting mode is interaction with the user. So the plugin here sends full list of goals. Then Actema will render the goals as an HTML DOM tree so that the user can manipulate it. So the user will start some gesture, typically drag an item or open a contextual menu. And then Actema, from this gesture, will compute a list of possible actions that you can use. And so the user will pick a specific action by ending the gesture, so dropping an item or clicking on the menu. And then you get an action, actually a pair of an action of integer which represents the focus of the current subgoal. And then you redo. So then the plugin compiles the action and sends a new list of goals, and you do this in a loop until you're done. So how do we compile actions? Actually, I haven't done this part. It's my PhD advisor, Benjamin, who did, with the help of Kostov, who gave useful insights. So click actions are just standard Coq tactics. That's why they give nice proof terms. But drag and drop actions have a more complicated semantics. And so we had to write around 3,000 lines of Coq and LTAC code. Basically, we do a deep embedding of the goal in first-order logic. Then we have a bunch of tactics which take as input the selection of subterms as a list of paths, which are themselves a list of nats to choose, like the subterm. And then we use computational reflection to compute the result of drag and drop actions. So, and the final step is to have a soundness theorem which relates the input to the output. Yeah, 5 minutes? Okay. And then we apply the soundness theorem to get the final tactic. So to conclude, we think the most useful use cases of Actema are, as I said earlier, proof exploration. So what you want is not some full automation, but to allow the user to explore freely the structure, the logical structure of the goal, and sketch some partial proof. And we also think that it could be very useful in an educational setting, like the one we've seen earlier with ZFC, because the syntax of tactics is a lot more intuitive, we think, and uniform than learning a bunch of different tactics. So there were a handful of infrastructure challenges and solutions. Just to mention a few of them, so we had to have a portable API to communicate between the plugin and the interface for communication protocol. And to do this, we use ATDGen, which is a language to specify data API. And it has bindings to OCaml and other languages to generate the boilerplate for serialization. And also, we've had some technical problems with linking external libraries in the Coq plugin, which are used to handle HTTP communication and serialization. And so we cannot use Dune to build our system currently. This is all based on some previous works. So just to mention a few, there is proof by pointing in the 90s, which already had this idea of clicking on subterms to build inferences. There is also subformula linking from Kostov, which is really the foundation of the semantics for drag and drop actions. And then you have this recent work of Ayers called Proof Widget. So it works in the lean proof assistant, But so it has similarities with our client-server architecture, but the aim is quite different because in their framework, this is a proof assistant which generates the graphical user interface instead of requesting actions from it. And so many lines of future works, like currently we cannot handle Coq notations, and this would be really necessary to handle more complex theories. But there are some non-trivial questions because we need some interactive expressions, but Coq can give either a concrete string, like pretty printing of the terms, or an abstract syntax tree. So we don't have the concrete syntax tree. And also, we'd like to apply this idea of drag and drop to filter results in lemma search. Like you can select a subterm, and then it will suggest only lemmas which can be used in a drag and drop action. And finally, we would like to extend this to the full higher order logic setting to handle more complex settings. And also, there is another line of work in proof evolution. So we could translate graphical actions to textual tactic invocations. But this will require some work to have something which is readable and reusable. And also, we could imagine like replaying and editing the proof, the graphical gesture sequences, with some animations. So thank you for your attention, and don't hesitate to ask questions.
So in the tool, can you apply previously proven lemmas or only things that are in the context?
Sorry?
Can you apply previously proven lemmas or only things that are currently in the context?
Oh, no, you can, like, okay, you cannot, in the graphical interface, search for lemmas currently, but this is something we're going to add. But currently, you have to, in Coq, in the proof script, pose the pose proof to get the lemma in your context. And then,
Cyril Cohen in RIA. I was wondering, so in my personal use, I don't think I would like to use the graphical interface, but the deep substitution, absolutely.
Okay.
So I was wondering, I think that's a bit part of the proof evolution item 1, compact language to do the same without relying on the graphical interface. Is
So
it something you plan to do?
It's completely doable. Like our colleague Kostyev has done this, like in Lean. So actually, he can export this kind of drag and drop actions and compile them to Lean tactics. And in Lean, he designed an interface like custom tactics, which take the path to the subterm as an argument. But I think this is not very readable and reusable to have explicit manipulation of path. If your context changes a little bit, it can break easily. So, but this is possible. Yeah.
To answer this remark, you should look at the pattern language that's used in MathComp.
Okay.
That would give a way to be very precise without having to deal with paths and positions.
Okay.
And the second remark or question is, I'm very wary about the fine motor skill that is needed to do the drag and drop action.
Yeah, it requires a bit of training.
And do you have ways of did you start to think about ways to avoid this kind of burden on the user?
So we haven't really thought about, like, we know this is a problem, but we haven't really investigated how to improve this. But basically, you could imagine just pre-selecting, as I do for induction, for example, you pre-select the subterm, and then you don't have to be very precise, and then you can just apply some, I don't know, press some key to apply the drag and drop, you know. But
okay, last question. Thank you, great talk. So just tying into what Cyril was saying, if you could do these deep rewrites by just dragging things from the actual Coq goal, that would be amazing. But right.
Yeah, but that's a bit more complicated.
Yeah. Anyway, so for teaching, I mean, I think the graphical thing can be great. A worry there, but this is a worry even when I teach software foundations. is that the students just pattern match on the goal and apply destruction and intros and whatever until eventually Coq says, yes, you're okay. But nothing was learned along the way, right?
Yeah, I think.
Do you see a problem here with that as well, or do you have any suggestions? Because I don't, about how to make this better.
I think maybe if you really want to teach the very basics of logic and logical rules, maybe the framework we've seen earlier, this ZFC thing, is a lot more adequate. But also, if you want to teach the joy of proving and like how do you say it? Like teach this as a game, I think this is an important part of what we like also about proof assistance. Is like we feel like we're playing some game, and so I don't think we should completely dismiss this. But yeah, those are two things in tension. But yeah, you could do this. You could have some scoring function, or I don't know.
All right, let's thank the speaker.